And let me share the screen. Get into that. I thought I'm already in. Mm. How come I'm not in? Okay, I'm gonna share the screen. Okay, where were we last time? Last time we finished classification of signals, right? Okay. What page was it? We did. Oh, we haven't finished yet, right? We still have the last two, bounded, unbounded, and energy and power signals. Okay. Shall we start? Are you ready?
Yes.
Yeah. Okay. No way. It's not that energized as the previous class, huh? Mhm. Okay. A signal can be bounded or unbounded. What does it mean? Okay. A signal is xt is bounded if absolute value of xt is less than infinity. Okay, absolute value of xt is less than infinity. Otherwise, it could be unbounded. For example, x1t is e to the 50. What does it mean, e to the 5t? What does it look like?
Just go on and
X1.
on.
Well, how do you plot the graph? This is xt, right? So we're going to have exponential rise, right? Exponential rise. What's the slope at t equal to 0?
5.
Uh, it's going to go past y, vertical axis at 1, right? The slope is 5. So it will cut at -5, right? Okay, this is the slope. Okay, and you can see here, this graph goes to infinity. Okay, you can see that absolute value of xt goes to infinity, okay, as uh, as t goes to infinity, okay. So therefore, this graph is unbounded. Okay, it's that easy. Okay, how about x2t? X2t is side 3t, right? How do you plot side 3t? This is t, this is x2t. Side 3 looks like what? It's just the sinusoid function, right? Sinusoid functions. What's the period? What's the period? In this case, omega is 3, right? Which is equal to 2 pi, 2 pi over t. So t is 2 pi over 3. So one period, okay, one period would be what? 2 pi over 3. Okay, next period would be negative 2 pi over 3. And what's the height?
1.
1. What's the what? The lowest value is -1. So you can see that it's bounded by what? It's bounded by -1 and 1, right? You can see that Psi of 3t is between negative 1 and 1. So it is bounded. Okay, that's it. Okay, a signal will be bounded. It is does not go to infinity anywhere. Okay, that's easy. Okay, how about energy and power? Okay, a signal with finite energy is called the energy signal. Okay, and the signal with infinite energy but finite average power is called the power signal. Okay, uh, actually there should be the signal with infinite power. Okay, the infinite power, usually the real signal, it does not have infinite power. Okay, because if it has infinite power, conservation of energy doesn't work, right? You can How can you get infinite power? It's impossible. Okay, usually the real signal, in practical signal, doesn't have infinite power. Okay, if it does have infinite power, it's neither an energy signal nor power signal. Okay. Okay. What does it mean by energy? Okay. A signal, the energy of signal is defined as this one. Okay. Actually, it's come from electricity, right? Usually a signal, okay, it's like square. Okay. Its power is square. Okay. It's a square of the functions. Okay. And if you integrate this one is the power. So actually, no, right? Actually, the power is x squared and then divided by t. That's the power. Okay. That's the power. Okay. Or you integrate the whole thing, right? The square and integrate the whole thing. That's the power. Okay. So energy would be the integral of the square of x. Okay. Just follow these definitions. I'm sorry. This is wrong. Okay. Just follow these definitions. Okay. This is the definition of energy. Okay, if you integrate x squared, absolute x squared, okay, from negative infinity to infinity, okay, you integrate for the whole t, okay. But be careful here a little bit, okay. If it's real, it's okay. If absolute x t squared, okay, if x is real, it's just integral of negative infinity to infinity dt. Okay. However, if x is complex, it's equal to integral from negative infinity to infinity, but absolute x squared, if x is complex, is equal to xt times x conjugate t dt. Okay. Be careful with that. Okay. It's got to be x if x is complex. This is if xt is complex. Okay. It's going to be integral of x times x conjugate dt. Okay, this is the equation for energy of X. Okay. Well, normally we're gonna encounter this when we learn the Fourier transform. Okay, in frequency domain, you're gonna have complex energy. Okay, you're gonna have complex energy. Find the complex through the frequency domain. Okay. The average power of the signal, this is called the average power. Okay, average power of the signal, if it's periodic. Okay, if a function is periodic, it's just the integral of xt dt. Okay, this symbol means integral from 0 to t. Okay, this symbol means dt. Okay, it means you can start from anywhere t naught. Okay, and then you integrate for one period t naught plus t dt. This is what it means. Okay, t naught could be any time frame. Okay, any constant, any time instance, right? Okay, this is what it means. Okay, when I write it like this. Okay, it means just integrate over the period regardless of the starting point. Okay. And if it is periodic, you got to divide it by the period. Okay, you got to multiply by 1 over t. Okay, if it's the periodic. If it's non-periodic, okay, suppose if you got a function that is non-periodic, okay, suppose you got a function that is non-periodic like this, okay, first you think of it as what? From negative, integrate from negative t over 2 to t over 2, okay, like this. And then you extend this t to infinity, okay, and then you extend this t to infinity, to negative infinity. So that's why we integrate from negative t over 2 to t over 2, okay, and divided by t, capital T, right? No, the whole time here is t, right? Divided by the whole time t, and then you take the limit as t goes to infinity, okay, and then you take the limit as t goes to infinity, okay. Okay, let's take a look. Oops. Okay, let's take a look. Identify the energy signal and the power signal among these three signals, okay, with x1, x2, and x3. Okay, let's take a look at x1 first. T, okay, x1t, okay. x1t looks like what? It's equal to t for t, absolute t less than 1. What does it mean by absolute t less than 1? What does it mean by absolute t less than 1?
The domain defined from the range -1 to 1.
Right. It's defined as a range from -1 to 1. So only define between -1 to 1. Okay. So xt equal to t, what does it look like?
A line.
Just a straight line. Okay. Passing through the origins and start here and not including this, right? Okay. Okay. It looks like this. Okay. And how about when t is more than 1 or less than -1? What happened? Well, it's not defined, right? So this is a finite support, okay? But we can assume that it's equal to zeros otherwise, okay? We could assume it's equal to 0 otherwise, okay? So we could assume 0, okay, otherwise. Okay, we could assume. This is 0 padding, okay? We could assume that, okay? Now, is this function an energy function? Okay, so first of all, we find energy of x1. Okay. Okay. What is the energy of x1? Is the energy of x1 by definition is equal to integral from negative infinity to infinity absolute value of x1 t squared dt, right? Which is integral from negative infinity to infinity. But this one xt dt, okay, x1t is equal to what? Is equal to t, right? So we got absolute t squared dt, but t from -1 to 1. That's it, okay? That's how we define. Okay, that's how we define this, okay? And what do we have? How do you integrate this? It's just t squared, right? So we got 3 cubed over 3 from, oh, this is an even function, right? This is an even function. What do we have? Since t squared is even, okay, this is even. We can say that it's equal to twice the integral from 0 to 1 t squared dt, okay, which is twice t cubed over 3 t from 0 to 1, which is 2/3. Okay, so it is finite energy, right? It's less than infinity. Okay, it's less than infinity. Therefore, this signal has finite energy. Okay, this is the energy signal. Okay, this is an energy signal. Hold on. Okay, next is x2t. Okay, x2t is that an energy signal. What's x2t? Psi t. Psi t. Okay. X2t, psi t, what does it look like? It's just what? Sinusoid, right? It's bounded sinusoid, but it goes infinity, right? It goes to from negative infinity to infinity. Okay. And if you want to integrate, okay, if you want to integrate x2, is you are integrating psi t, quantity squared dt, right? From negative infinity to infinity. And you can see here, if you integrate this, this is x squared t, the ones goes here, and the two, if you square, it goes like this. Okay, this is absolute psi t square. Okay, absolute psi t square, and if you integrate from negative infinity to infinity, you can see that it all has positive area underneath. Okay, so what do we have for this one? If you're integrating psi t squared from negative infinity to infinity,
Infinity.
it's infinity. Okay, you got infinite area, so definitely is not energy signal. Okay, now we got to check whether or not it has what? Whether or not it is a power signal. Okay, if it's a power signal, you check for the average power of x2. Okay, since this one is periodic, what is the period of this psi t? What's the period of psi t?
2 pi.
0 to actually omega is equal to 1, right? Which is equal to 2 pi over capital T. Actually, T is 2 pi. Yeah, it's 2 pi, right? Okay. So in this case, we're going to have what? 1 over 2 pi. Okay, that's 1 over T. Okay, according to the definitions here. Okay. And then integrate just one period. Okay, just one period from 0 to 2 pi. Okay, and then psi square t dt. Do you know how to integrate this? How do I integrate this?
Change psi square to uh, 1 minus cos 2t divided by 2.
Okay, so we got 1 over 2 pi integral of 1 minus cosine 2t, the whole thing divided by 2, right? dt from 0 to 2 pi. Okay, go ahead and do that. What do we have? The 2 can come out, right? Can come out. So we got 1 over 4 pi. Integral of 1, which is t. And integral of cosine 2t, we got sine 2t over 2, right? T from 0 to 2 pi. So we got 1 over 4 pi. T is 2 pi, so we got 2 pi minus 0 minus sine of 4 pi. Sine of 4 pi is 0, right? Yeah, okay. So we got 1/2. Okay, and it's of course less than infinity. Therefore, psi t is a power signal. Okay. Okay, next. Okay. Next is x3 t, which is e to the t. Can you follow that? Okay. x3t, this is t, this is x3t, which is e to the t. What's e to the t looks like? Is exponential rise, right? The slope at t equal to 0 is 1. Okay. So it goes to -1. Okay. This is the slope. Okay. Slope. Okay. That's e to the t. If you are to integrate e to the t square, right? If you are to integrate e to the t square dt from -infinity to infinity, of course, you're going to get what? It's unbounded, right? This one is unbounded, so it's not the integral is infinity. Okay, so it's not an energy signal. Okay, it's not an energy signal. Now we want to find the average power. Okay, how do you find the average power? Well, we start with what? Integrating along, okay, from -t/2 to t/2, like this. Okay, that's the whole period t. So in this case, we says the power of x3 is equal to the limits as capital T goes to infinity, 1 over capital T, okay, integral from -t/2 to t/2 of what? E to the 2t, right? That's e to the t quantity square, dt. Okay, that's what we have. So we have limit as t go to infinity, 1 over t. This one, we take the integral e to the 2t. We got e to the 2t over 2. From -t/2 to t/2. So we got limit as t goes to infinity, 1 over t. What you have? E to the capital T, right? E to the capital T minus e to the what? Negative capital T over 2. The question is, and this is, so this is the 1 over t goes inside, okay? The question is, if t goes to infinity, okay, what does this go to? You can see e to the infinity over to infinity, okay? This one, e to the infinity goes to infinity a lot faster than t goes to infinity, right? You understand that? You know why? Because e to the, you can see if you expand e to the 2t, right? If you expand e to the t, okay, if you expand e to the t, is approximately what? Have you learned the Taylor series? What's the Taylor series for e to the t? 1 plus t squared over 2 factorial plus t third over 3 factorial, and so on, right? And if it's divided by 2t, okay, the whole thing divided by 2t, you can see that this is what? 1 over 2t. This one is goes to 0, plus 1/2. This one go to 1/2, but this one t over 4 and t squared over 6 and so on. And you can see that all these terms go to infinity as t goes to infinity. Okay, therefore this whole thing goes to infinity. Okay, so the average power goes to infinity as well. Okay, therefore this one say is neither. Okay, neither energy power or average power. Okay, this one has infinite power. Okay, has infinite power. Okay, we finish this. Okay, we're gonna talk about this a little bit later on. Okay, when we prove we just use it to prove something. Okay, we need to prove that the energy in the time domain is equivalent to the energy in the frequency domain. Okay, that's all. Okay. Okay, let's learn the new thing today. Okay, what we're gonna learn today is some important continuous time signal. Okay, and then we're gonna learn the discrete time signal later. Okay, what's the most important signal that we're gonna learn today is this one, unit impulse signal. Okay, the unit impulse signal, sometimes we call it the direct delta function. Direct is the name of the person who invented this. Well, I think. Okay, direct is the name of the person. Okay, sometimes we call it the direct delta function. Okay, a direct delta function is defined as this. Okay, a delta function is defined as 0 as t is non-zero and equal to infinity as t equal to 0, such that, okay, integral from delta t dt equal to 1 from negative infinity to infinity. Okay, what does this mean? Okay, this is what it looks like. This is the graphs looks like. Okay, it's equal to 0 here. It's equal to 0 for t is non-zero. Okay, except for t is 0, right? And it's supposed to go to infinity. Okay, this one goes to infinity. Okay, here. Okay, it's like this. And it goes to infinity. This one goes to infinity as t equal to 0. But how come there's a 1 here? Okay, a 1 here tells us that actually the value of delta function at t equal to 0 goes to infinity. But the one here, the length of the arrow, okay, we use the arrow to represent the delta function, okay, the direct delta function, okay. But the one here represent this one, the area under the curve, okay. Actually, the real thing supposed to be like this, okay, supposed to look like this, okay. And the area under it is 1. Okay, the delta functions. Okay, there are many representation of the delta functions. Okay, well, but this one is the one we use mostly. Okay, sometimes I don't really draw the 0 line here. Okay, sometimes I don't really need these 0 lines here. Okay, most of the time when I draw the delta function, I just draw like this. Okay, that's it. Okay, so you assume that the rest are 0 anyway. Okay, it's like you could think of it as finite support, okay, instead of infinite length, okay, with 0 padding. Okay, okay, where does it come from? Okay, this is what we're gonna have. Okay, here we call it the regularized unit delta function. Okay, the regularized unit impulse signal. Okay, regularized means is this one. Okay, delta with subscript epsilon. Okay, it's equal to 1 over epsilon. Okay, that means the height is 1 over epsilon here. The height is 1 over epsilon here. For absolute t between epsilon over 2. Absolute T less than epsilon over 2. So the height is 1 over epsilon. For the width is epsilon negative epsilon over 2 over epsilon over 2. And you can see here the area under the graph. How much is the area under the graph? What's the width here? What's the width here? What's the width here?
Epsilon.
Epsilon, right? And the height is 1 over epsilon. So what's the area under the graph?
1.
1. Okay, which is correspond to this one. See, this one means the area under the graph is 1. Okay, which is the same thing except the width here. Okay, this one, if we narrow down, okay, remember the area of under the curve, okay, the area under delta function got to be always equal to 1. Okay, from this picture, okay, from this rectangle, this looks like a rectangle, right? Okay, for this rectangle, if I take the limit, if I take epsilons go to 0, what happened? Okay, like this. If I take the limits, okay, as epsilons go to 0, okay, let's see. If I take the limits as epsilons go to 0 of this delta function, you can see that the width here is getting smaller and smaller, okay? But the height got to be what? The height got to be taller, okay? To keep the area under the curve to be 1, okay? To keep the area under the curve to be 1. Width is smaller, height got to be higher. The area under the curve is a constant 1. What happens if epsilon goes to 0? What's the height going to be? If
Infinite.
epsilon goes to 0, if the width go to 0, of course, the height is supposed to go to infinity, right? And that's how the delta function is defined as the arrow, okay? It's defined as an arrow. But we specify the length of the length of this arrow to be 1, just to mean that the area under the curve is 1. Okay, so in this case, okay, this is why it says we may think of the direct function as the limit of the regularized unit impulse as epsilon goes to infinity. Therefore, in this case, the limit of epsilon delta epsilon t from epsilon go to 0 is just delta t. Okay, suppose if I give you something like this, t, delta t. Well, actually, this is not delta t. This is just a x-axis anywhere. Okay. Suppose I draw something like this. The height is 2. What does this mean? What is this function? Everywhere else is 0. What is this function? Let's call it x1. x1. What's x1 supposed to be equal to? It's going to be equal to what? It's equal to according to this, is equal to what? To 0 again, right? As t is non-zero and is equal to infinity as t equal to 0. Such that what? The integral of x1t dt from negative infinity to infinity equal to what?
2.
2. Okay. And how do you know that? Well, I could just say is that this is actually equal to 2 times the integral from what? From negative infinity to infinity of delta t dt, right? Because integral from of delta t dt is just 1, okay? And I can put the delta, the 2 in, so I got integral from negative infinity to infinity of 2 delta t dt. And if I compare this expression with this expression, I will say that x1t is just 2 delta t. Okay, so the 2 here represent this 2 that multiply with the delta function. You get that? Okay, good. Now let's see some of the property of impulse, unit impulse signal. Okay, this is a continuous time impulse. Okay, there is another impulse signal called the discrete time signal. Okay, which is slightly different from this. Okay, we're gonna learn it later. Okay, in the following weeks. Okay, the first property of unit impulse signal is that it is an even function. Okay, it must be an even function. What does it mean by an even function?
The delta negative t equal to delta t.
Exactly. Delta negative t must be equal to delta t. Okay, it got to be symmetric over the vertical axis. Okay. The second property is called the scaling property. Okay, the scaling property. Well, we'll come back to this one later. Okay, this one means we'll come back when we learn scaling. But right now, you just remember this. Okay, this one means you squeeze by 1 over t, then the delta t, the function will goes down. Okay, well, I can tell you right now is like this. Well, if you got a rectangular functions, okay, suppose it's just like going to the rectangular functions. Okay, suppose if we got a rectangular function xt, in this case is our what? Is our delta, well, I just draw it, exaggerate it a little bit, right? Delta of epsilon t, okay? When we learn the scaling, which is next class, okay? Delta of at, okay? If a is more than 1, okay? For example, delta of 2t, suppose if delta of 2t, then it's gonna look like this, okay? It's gonna get squeezed. Okay, it's gonna get squeezed. Okay, if suppose this is from what? This is from epsilon, negative epsilon over 2. This is epsilon over 2. If this delta 2t is going to be epsilon over 4. And this is epsilon over 4. Okay, it gets squeezed. Okay, the height is still 1 though. Okay, the height is still 1. But this one, I'm sorry, this is the height is 1 over epsilon, right? The height is 1 over epsilon. The area here is 1. Okay, but this one, the height is epsilon, but the area underneath it is what? What's the area underneath this?
Half of epsilon.
Right, it's epsilon over 2, right? Okay, now if you want to represent, if you take the limits as epsilons go to 0 here, what do we get? If epsilon goes to 0 here, of course, the value, the height going to go to infinity as well, right? Okay, the height going to go to infinity as well, but the area under the curve is epsilon over 2. See? Okay, will be half of the original. Okay, half of the area here. That's why, therefore, this one will be 1/2 of epsilon t, of delta t. Okay, I need to, hold on, I need to plug in the, the computer. Okay, 1 second. Okay, all right, okay. So that's why we have this property. Okay, actually, we're gonna have absolute value as well. Okay, we'll learn that later. Okay, we'll understand it better later on. Okay, but at this point, remember this. Okay, the next one says for any signal xt, if you multiply xt by delta t, okay, for example here, okay, this, the blue line is xt. Okay, xt is the blue lines. Okay, delta t is the what? Is the orange arrow. Okay, and this orange arrow here is 0 otherwise, right? It's equal to 0 otherwise. Okay, this is what we're gonna get. When you multiply this, everything else gonna be multiplied by 0, except for at this, at t equal to 0, it's gonna multiply by delta t. Right? So if you got xt multiplied with the delta t, what you get would be just delta t, see, multiply with x0. Okay. In other words, when you multiply with x zeros, okay, but x zero is just a number now. It's just like this one, right? It's just like this one. In number 2 here, just multiply by number 2. Therefore, it means it changed the length of the arrow. The length of the arrow is just x0. You see that? Okay, the length of the arrow becomes 0, become x0. Okay, if you multiply these two, the blue line, okay, if you multiply the blue lines with the orange orange arrow, you're gonna get an orange arrow, but the height is different. Okay, the height got to be just x0 according to this one. Okay, according to this one. Okay, next is this one, which also implies if you multiply xt, which is the blue lines here, xt, xt, xt is this blue lines. If I multiply with the green arrow, the green arrow is the shifted delta function. Okay, the shifted delta function is shifted to t naught. Okay, again, okay, if you multiply this arrow with this line, everywhere else going to be 0 except for at t equal to t naught, right? Except for t equal to t naught. But it's going to be the arrow, right? It's going to be the arrow, okay? Multiply with the arrow delta t minus t naught, multiply by x at t naught. You see that? Okay. Therefore, according to these pictures, okay, that's how we're going to get, okay, is you now multiply two delta functions, okay, of course, at this one means the height here is 1, okay, this height here is 1, okay, you're going to get delta functions, okay, you're going to get delta functions, and the height of the arrow changes according to that value of the functions, okay. We're going to use this, okay, when we learn sampling. Okay, we use this when we sampling. Okay, sampling a continuous time signal. Okay, when we are sampling a continuous time signal, basically we have a bunch of delta functions, okay, periodic delta functions like this. Okay, if we got another periodic delta function like this, then the high here gonna be this one. Okay, this is negative T naught. Okay, so we sampling the continuous time signal by periodic delta functions. Do you understand? Okay, so this one, number 3, is very important. Okay, put the stars in. Okay, you remember that. Okay, it might come up in the quiz later. Okay, next, okay, we can use this property, okay, to integrate. What happened if we integrate these functions? Okay, remember here. Okay, if we want to integrate xt delta t minus t naught dt from negative infinity to infinity. Well, of course, we learn that this integral becomes just the integral from negative infinity dt. What is it inside? What's inside the integral?
Uh, it will be xt0 xt0
Xt naught
times with uh, delta t minus t naught.
delta t minus t naught. Okay, which is, and now you can see xt naught is now just a constant, right? It doesn't depend on t anymore. What can I do? If it's just a constant, does not depend on t,
Pull it out of the integral, and the rest is
right?
1.
Right, exactly. We pull out the integral and we integrate the delta t minus t naught dt. But remember, the integral of delta t dt from negative infinity to infinity is 1. Therefore, what's the integral of xt times delta t minus t naught dt? Is just
xt0.
x at t naught. What is x at t naught? It's just a number now. So that means over here, if you integrate these values, right? If you integrate the value, you get x t naught. If you integrate this value, you get x at t, x at 0, and this one is x at t naught. Okay? This one, we call it the shifting property. This one, okay? This one is called the shifting property of the direct delta function. Okay. It shifts the value of xt. Okay, it shifts just the value of xt at t naught. Okay, xt at t naught. Okay, it shifts the value of xt at t naught. For example, suppose if I have a functions and I want to know what is this value of x. What do I do? Suppose this is at 2, at t equal to 2. What do I do? I integrate, right? This is xt, right? I integrate xt, that is multiplied by what? If you want to extract the value of x2,
Direct
if you want
delta
x2,
delta t minus 2.
right, delta t minus 2, and integrate from negative infinity to infinity. That's how you get the value of x2, right? Okay, if you want x3, you just have what? x3 would be integral of x2, xt, delta t minus 3 dt from negative infinity to infinity. You see? So you multiply by delta functions and then you integrate it, you got the value back. You get the value of xt. And that's really how we do sampling. Okay, that's how we do sampling. Okay, we'll talk about that later on. Okay. The last one, however, is very important. This is called the convolutional property of unit impulse. Okay, we're gonna learn about the notation of the convolution. This symbol means convolutions. And by definition is equal to integral from negative infinity to infinity x tau, delta of t minus tau d tau. What is it equal to? See, this is a tau, this is a tau. Well, actually, this is different. There's a t here, and this is a d tau now. So what is this equal to? Does it look like this? Not yet, right? T becomes T naught and tau becomes T, not quite. Okay. But we can change it. Okay, we can change the definitions. Well, we can change the notation a little bit. Okay, we can change the notation a little bit. How do I change the notation a little bit? Oh, I see. I see. I use the fact that this one is tau minus t. Why? Delta t minus tau, how come is equal to delta tau minus t?
Even function property.
Right, because delta t is even. Okay. And now if we integrate x tau t of t minus tau, tau minus t d tau. From negative infinity to infinity, what do I get? Same as the one above.
X tau.
X, not x tau,
XT.
xt. Wow. What does it mean? Okay, this is called, when you got xt convolute with delta t, you got xt back. Okay, you got xt back. Okay, oops, I erase all of them. Okay, this one means this one delta t is the identity. Okay, is the identity of convolutional operator, right? We call it the identity of the convolutional operator. Okay, the identity of the convolutional operator is just delta t. It's just like when you have identity of adding, right? Suppose you got a plus 0 and is equal to a. What do we call the 0? The
Identity
identity
of A.
of plus, right? If you got what? A multiply 1 equal to a, what do we call 1?
Identity of multiplication.
Right, identity of multiplications, right? If you got a times I equals to a, that's the matrix, right? This I is the identity, multiplicative identity, right? Multiplicative. identity. We learned it in advanced mathematics last semester. Okay, so the identity for the convolutional operator is the delta t. Okay, delta t convolute with any signal, you got that signal back. Okay, it's that easy. I believe I have set up the quiz to come up at 11:40. Okay, so we have about 12 minutes. Okay, let's finish this. Oh my gosh, you just go through impulse train. Okay, what's an impulse train? Impulse trains, I represent it by delta t with the subscript capital T. Okay, delta t with subscript capital T. Okay, okay. This one is just summing, right? We summing delta t. It's just like this, right? This is summation, so it's like this. Okay, it's delta t plus what? Delta t plus t plus delta t plus 2 capital T, and so on. And this one on the left is plus delta t minus t, right? Plus delta t minus 2 capital T, and so on. Okay, that's how we get, right? This one is just delta t. This one is delta t minus t. This one is delta t minus 2t, right? This one is delta t plus t, and so on. Okay, so we call it the impulse train. Okay, we call it the impulse train because it's a train of impulse. Okay, it's a train of impulse. And this one is used when we want to do sampling. Okay, I'm gonna talk to it again later. Okay, but today we're just gonna do everything here. If suppose I got x of t, okay, if suppose I got x of t, and what do I do here? You go back to this one, right? To this signal. Okay, if I do x of t and you multiply x of t by the impulse train, okay, this one goes to x of t multiplied with the impulse train. What would you get as the output? Can you draw the graph? This is x of t multiplied with the impulse train t. What would you get?
Well, it's like a discrete signal, something like that.
It's going to be signal like this. Actually, it's just another impulse train, right? But the height is different. Okay, the height would be different. Okay,
Uh,
according to xt, right? The height will be different according to xt. And if I make it go through, okay, make it go through and integrations dt from negative infinity to infinity, if I integrate this, what would I get? This is
sum
the
of
integral of x. What's that?
x, sum of xt at each of the impulse train.
Right. Actually, this is integral, right? It's going to be, it's just, this is xt, okay? It's just going to be that value, okay? Now it's changed from arrow to that value, right? Because we just got that, we got the integral, right? If you take the integral, it's just going to be stem value. And this is our xn, okay? This is how we do sampling. This is the from continuous time to discrete time. Okay, CT, I call it CT to DT converter. Right? How about CT to DT converter? Okay, we use impulse train to do discrete time converter. Okay, all right. The next one.
Can I
The
see the
next one.
equations the most
What's
left
that?
again?
What's the
There was
equation?
an equation on the most left graph. Yeah. I,
The equation on the most left graph. This one?
no, no. The sampling after you convert it.
The sampling. This one? Oh, this
The
one.
one to the right of it. I cannot
Oh,
see
the
that.
one to this one?
Yeah, that's the most right, right?
Yeah.
So what's the difference from the one before it? I cannot see
This
it in
one. This
equation.
one does not have any integration. This one, the one on the left here, does not have integration, just multiplications. This one has integrations.
So like, so so the middle one is more like a dot
Impulse.
and
No,
oh,
it's impulses. The middle one is the impulses.
uh-huh, yes.
Once you integrate it, you got a dot.
Ah, okay. Thank you.
Okay? Mm-hmm. Okay? Clear?
Okay.
All right. Good. Wow, we learn a lot. Okay? It's got 4 minutes left. Okay, doublet. Doublet is the first derivative with respect to time of the impulse signal, delta t. Okay, doublet is basically d by dt of delta t. Okay, wow, what is a doublet? Okay, d by dt of delta t. Okay, like I told you, okay, well, okay, let's go back to the regularized delta t first. Okay, remember the regularized delta t. This is delta t e to the negative delta epsilon over 2. This is delta regularized delta t, right? If I want to find the derivative of these functions, regularized delta t, what does it look like? What would it look like? You know how to take the derivative? This one, you got
May
zeros, right? There's no
is
change.
is it look like the impulse train, something like that? Two
No,
impulse.
not quite. What's the derivative means with respect to t? The derivative means the slope. right? So
Yes.
what is the slope of this graph?
Infinity.
Infinity. Okay, so actually the slope goes to infinity at negative epsilon square. And over here, what's the slope at this area? Zero.
0.
And what's the slope at this area? At epsilon over 2?
Negative infinity.
Negative infinity. The question is, what's the height? And when we take the epsilons, when we take the limits as epsilon goes to 0, when we take the limit as epsilon goes to 0, what is this graph should look like?
Up and down arrow at t equal to 0. Something like
Yes,
that.
it should look like this, right? But how do you know which one goes up, which one goes down? Okay, the notation should be this. Okay, see, it's so weird, huh? The notation should look like this. Okay, it should go like this, go down, and then like this. Okay, just have an arrow on the left. Okay, undo. Okay, just have an arrow on the left. That means it's go up first, and then have an arrow to the right. It means go down after. Okay, these two combined, you got this one. This is supposed to be delta t, delta prime t. How about negative delta prime t?
Just from the exact opposite sides.
Yeah, well, you flip this, right? Up and down. So we got this. Okay. But this notation, nobody use it. Okay. Only I use it. Okay. I invented it myself. Okay. Hopefully in the maybe in the futures, you guys using it, please refer to my notation. Okay. This is called Chan Chai notation. Okay. But I can see that it can be very confusing, right? This can be very confusing. Thank you. Thank you. Okay. I never seen any book use this notation. I use it myself. Okay. But I'm too afraid to put it in here. Okay. Oh, I think the quiz is coming up. Okay. So actually my notation would be I delete this part. Okay. I delete this part to make it more recognizable. Okay. So instead of this, actually my notation would use this one for delta t. Okay. For delta prime t. Okay. For delta prime t, positive delta prime t looks like this. Okay. And negative delta prime t looks like this. Okay. This is negative delta prime t. Okay. I erase this one. Okay, that's my notation. Okay, if you take a look in any books, nobody ever used it yet. Okay, only me, only in this lecture. Okay, only in this course that use these notations. Okay,
I
all
have a
right. What
question.
is, yes, yes,
Uh,
sure.
so is this still so is this still considered as like one impulse? Or
Actually, it's the real one looks like this. Actually, this is like an impulse. Actually, two impulses. Well, but we call it we call it one doublet. One doublet.
okay,
It's
okay, I
not an
see.
impulse. Okay, we call it a doublet function. And the real one looks like this. Okay, this is the real one, but this is the notation I'm using. Okay, a doublet notation. Okay. And we could have the triplet notations. Well, the triplet would be, okay, somebody is calling. Okay. A triplet notation would be the second derivative of delta t, which is d squared by dt squared of delta t. Okay. Which is going to be, actually, if you take the derivative of this symbol, what do you have? What would you have? Oh my goodness. It's going to be what?
Up, down, up.
That's the triplet. And how do we represent this one? Okay, I haven't invented yet, okay, but we're not using it, so we just leave it like that. Okay, we don't ever gonna use that, so there's no happening. Okay, I think it's time for you to do, well, we can continue this later, okay, on Friday, unit step functions. I think the quiz probably don't have unit step functions, just delta function. Okay, I think the quiz has come up, right? Is it? Has this quiz come up yet?
Yes,ครับ. Yes, it has,ครับ.
Okay, yes, it has. So go ahead and do that. Okay, we continue this on Friday. Okay, finish this on Friday. Okay, you got 10 minutes, I think. Okay, until 11:10, 11:50 or something. Okay, to answer the questions. Okay, at this point, you have any questions?
Yes, may I ask something? For the page 11,
Page 11. Yes.
for the first line graph, uh, the graph for delta function that, oh yeah, the light one. So
The one on the right.
in fact, the length is infinity, isn't it? But the one that you show is show the area of the graph.
Exactly. The one here shows the area under the graph. Okay, the value itself goes to infinity.
Okay.
Okay. Mm-hmm.
And for the delta function of 2t, the graph that you write by yourself at the right.
On the right hand side.
Yes, why the area is epsilon divided by 2. Yes, it's this graph.
Yeah, because the width is squeezed, but the height doesn't change.
Why it is not 1 over 2? As the above one is at the area under the graph is 1. Why the under is not 1 over 2, but it is epsilon over 2. I'm not quite sure.
Oh, I see. I'm sorry. I wrote it wrong. It's supposed to be, the area is supposed to be 1 over 2. You're right. Okay. The area is supposed to be 1 over 2, not epsilon over 2. Okay. This one area is 1. So this one area is 1 over 2.
Okay.
Thank you for pointing that out.
And what
Okay.
about epsilon over 2 that you want to mean it? What do you
Well,
want to describe about epsilon over 2?
this one, so the area under 2, so the height is 1 over 2.
Oh, okay.
Okay. That's why you got 1/2 of delta t. Okay. The rest still the same. Just my mistake. It's supposed to be 1 over 2. Okay. Anything else? Very good. A very good questions for catching it.
Actually, Professor,
Yes.
I believe that the last question in the quiz is about the unit step, isn't it?
Oh, really? I didn't
Because
know.
it asks what is the assumed value of function of
Oh,
units at
okay.
0.
So I'll answer that. Okay. Okay. Here. Okay. Yeah. Okay. I'm sorry. I forgot. Yeah. Okay. Here. The unit step function, okay, is defined as 1 when t more than 0 and equal to 0 and t less than 0. The question is, what is u0? Okay, what's the value of u0? According to this, u0 can be any value between 0 and 1. Okay, can be any value between 0 and 1. But, okay, later on when we learn Fourier transform, we will find out that, okay, its approach halfway between, okay, it's halfway between 0 and 1. So actually it's equal to 1 for t more than 0, equal to 0.5 when t equal to 0, and is equal to 0 when t less than 0. This 0.5 come from u0 minus plus u0 plus divided by 2. Okay? So what's the value of this? Most book now assume originally, okay, originally it was this one. Okay, but there's a problem at u is equal to 0. And nowadays, most people prove that it's equal to 0.5. Okay, prove that is equal to 0.5. Okay,
Okay, thank
so
you.
that should answer the questions. Okay, so if you listen until the end of the class, you should be able to do the quiz. All right. Thank you. Okay, for paying attention. And we shall stop here.